Welcome to my second lecture for Philosophy 4400 about quantum mechanics. This lecture is going to be about the quantum formalism. Now first, why are we talking about the quantum formalism? Basically, this is because the philosophical issues surrounding quantum mechanics that people are debating about turn on the interpretation of quantum mechanics. And what this really means is the interpretation of the mathematical formalism. There are a number of different theories about what is the underlying reality, and what these different theories have in common is the same mathematical formalism, but they have different interpretations of what the mathematical objects represent and why the mathematical algorithm works. So that's what we need to talk about. We need to first understand what the formalism is before we can get into issues about how it should be best interpreted. So now, as some background, before we talk about how quantum mechanics makes predictions, we have to talk about these mathematical objects called vectors, because these are used to represent physical states in quantum mechanics. Mathematically, a vector is something that has a magnitude or length and a direction. You can think of this as an arrow in a space. It could be a three-dimensional space or two-dimensional or any dimensional. But you can think of it as an arrow, and the length of the arrow is the magnitude of the vector, and it's pointing in a given direction from the origin. You can also think of it as, you can think of a vector as being determined by a point in an n-dimensional space, and you can think of that as corresponding to the arrow that would be drawn from the origin to that point. You can also represent a vector by an array of numbers, which would be like the coordinates of such a point. And that means that you can represent a vector with a column of numbers, i.e. a matrix. There are a number of mathematical operations that can be done on vectors. So vectors can be multiplied by numbers, and the way this is defined is the product of an ordinary number with a vector is found by simply multiplying the number by each of the entries in the vector. So the constant c multiplied by this vector a1, a2 gives you ca1 and ca2. Okay, also you can add vectors together. So when you add the vectors together, that is equivalent to simply adding their different components. So you have this vector a1, a2, you add it to b1, b2, you get this. Notice that this, by the way, is a 2-by-1 matrix. There are two entries in it. The first entry is a1 plus b1. The second entry is a2 plus b2. In geometrical terms, this is equivalent to what they call the parallelogram law for the addition of vectors. It's equivalent to saying the sum of vectors a and b is the diagonal of this parallelogram that would be formed by having the vector a as one side and the vector b as another side of the parallelogram. Okay, you can also multiply two vectors together. There are two kinds of vector multiplication referred to as the dot product and the cross product. Here I'm talking about the dot product, also known as the inner product or the scalar product. So this is a way of multiplying vectors where you get a number, not another vector, as the result. Okay, and the way this is defined is if you have a vector A and a vector B, the dot product of them is the length of A multiplied by the length of B times the cosine of the angle between A and B. Okay, and by the way, this notation here, this is one of the ways that people sometimes represent vectors, by having this vertical line and something written here and then, a closing angle bracket there. When you write the dot product of two vectors, it's common to write them this way, having the opening angle bracket, the one vector, and then the other vector, and then the closing angle bracket. Okay, a couple of things that you'll notice about this. If you have two perpendicular vectors, then the cosine of the angle between them is going to be 0. The cosine of 90 degrees is 0. And so that means that when you multiply the two vectors together, when you take the dot product, you get 0. Also notice that if you take the dot product of a vector with itself, so a times a, that's just the square of the length of a. That's because the cosine of 0 degrees is 1. So you just multiply the two lengths together, and they're the same length. Okay, now all of this, this definition of the dot product is equivalent to doing this. If you have this vector a1, a2, and b1, b2, you can find the product of them by just multiplying the corresponding entries and adding those together. So multiply that by that, and multiply this by this, and then add the results together. Okay, now we have to talk about a thing called a vector space. So a vector space, mathematically speaking, is basically just a collection of vectors that satisfies these rules. So if you have a vector in the space, then if you multiply it by a constant, the result is also a vector in the space. Also, if you have two vectors that are in the space, you can add them together, and the result is another vector that's also in the space. And that's just defined to be true of a, quote, vector space. Okay, and this is important because the possible physical states in quantum mechanics are going to be represented as vectors in a vector space. Okay, now there's another interesting thing that we have to talk about called an operator. So basically an operator is just a function that takes vectors as inputs and it returns other vectors in that same vector space as outputs. Or you could say it's a mapping from a vector space into itself. These are some examples of possible operators. So it's the operation of taking any vector and multiplying it by 5. Or take a vector and rotate it by 45 degrees in a certain direction. Or take a vector and just automatically return the vector 5, -3, right, no matter what the input is. Those are all possible operations that you could do on a vector. There's a specific kind of operator on a vector that's called a linear operator. Most operators are not linear, but some operators are linear, and what that means is, just by definition, a linear operator satisfies these two characteristics. First of all, if you operate on a vector and then multiply by a constant, that's equivalent to first multiplying by the constant and then applying the operator. In other words, it doesn't matter what order you do these things in. It doesn't matter if you do the multiplication by the constant first or apply the operator. That's the first characteristic. The second characteristic of a linear operator is if you apply the operator to the sum of two vectors, that's equivalent to applying it to each of the vectors first and then adding them together. So it doesn't matter if you do the addition first, and then apply the operator, or you apply the operator first and then you add the results. An important mathematical fact about linear operators is that a linear operator in a two-dimensional space is equivalent to multiplying by a 2x2 matrix. That is, given a particular linear operator, there is a particular 2x2 matrix such that applying that operation is equivalent to multiplying by this 2x2 matrix. So these things, 011, 012, and so on, these are supposed to be numbers. So these are 4 numbers in this array. Now, the way that you multiply a 2x2 matrix by a 2x1 is like this. You do this row combined with this column to get the first entry, and then you do the second row combined with the column to get the second entry. So you do 011 times A1 plus 012 times A2, and that's the first entry here. This is a 2x1 matrix on the right-hand side here. Then you do 021 times A1 and 022 times A2. Add those together, and that's the second entry here. Okay, there's a specific kind of vector known as an eigenvector. So if you have an operator in a vector space, and if operating on a certain vector in the space is equivalent to just multiplying that vector by a constant, then that vector is said to be an eigenvector for that operator. And the constant here is said to be the eigenvalue for that eigenvector. In general, most vectors are not eigenvectors for a given operator. There's only a few special ones that are, although there are some cases in which there are for some particular operators, there will be a lot of eigenvectors, but usually there's only a few eigenvectors. And this is also going to have some important significance in quantum mechanics because the eigenvectors are going to correspond to definite states of certain observable properties. Okay, now here are some examples to illustrate and see whether you understood this definition of eigenvectors. So I'm going to read these questions and then I'm going to ask you to pause the video and see if you can answer them on your own, and then after that I'm going to give you the answers. Okay, so questions. What are the eigenvectors and the corresponding eigenvalues for the following operators? First, the unit operator, which is the operator that just multiplies a vector by 1. The operator that multiplies every vector by 5, or third, the operator that rotates any given vector 75 degrees about the vector A, that is taking vector A as the axis of rotation. All right, so pause the video and see if you can answer those. Okay, so I'm going to tell you the answers. So the first one, the unit operator has every vector as an eigenvector, and the eigenvalue is 1. Okay, so again, what that just means is this operator that multiplies every vector by 1 is equivalent to multiplying a vector by a constant. That's true for every vector that you apply it to, so every vector is an eigenvector. The eigenvalue is 1, of course. Okay, what about the operator that multiplies every vector by 5? Again, trivially, every vector is an eigenvector of that, and the eigenvalue is always 5. Okay, those were two trivial examples, but that was just to illustrate if you understood what I said about the definition of an eigenvector. Okay, this last one is a little bit more complicated. So you have an operator that rotates a given vector by 75 degrees with the vector A as the axis of rotation. This is a little bit less trivial. You might think, well, how would rotating a vector not change its direction, right? So the eigenvector has to be a vector whose direction is not changed by applying the operator. Only its magnitude could be changed, right? And if you think about it, well, the answer is the vector has to be pointing in the same direction as A. So any vector that is equal to a constant multiplied by A, including A itself, is an eigenvector for that operator. So if you rotate a vector around itself, then you don't change its direction. Okay, and the eigenvalue is 1 because you also don't change the length, so it's equivalent to multiplying by 1. Okay, maybe this will be a harder and less trivial question. So what are the eigenvectors and corresponding eigenvalues for this operator? Right, so it's the operator that is multiplying, it's equivalent to multiplying by this matrix, okay? So I want you to pause the video and see if you can answer that question, and then I'm going to come back and tell you the answer. Okay, so here's the answer to that. All right, so the way that we would answer this is by the definition of an eigenvector. This thing is an eigenvector if and only if it makes this equation true. And the C would be the eigenvalue. So the question is, what could be the values of A1 and A2 and C that would make this equation true? Because if this equation is true, then this is an eigenvector and that's an eigenvalue. Okay, and so just do the multiplication here. So the product of this times this is defined in this way. It's this times this plus this entry times that entry. And that gives you the first entry here. And then this one times that one plus this one times that one. Okay, so the product of this matrix with this vector is this thing. Okay, and then the thing on the right-hand side of the equation is just the constant times this vector, so it's CA1 and CA2. Okay, and so this thing on the left-hand side is just A1 and negative A2. Thing on the right-hand side again is CA1 and CA2. Okay, and so this equation implies that A1 has to equal C times A1, and negative A2 has to equal C times A2. So then, think about how that could be true. And if you think about it, the ways for these equations to be true are, so for this one to be true, for A to be equal to C times A1, A1 either has to be 0 or C has to be 1. If a1 is 0, then of course 0 is equal to a constant times 0. Also, if c is equal to 1, then of course a1 is equal to c times a1. Okay, for this second equation to be true, negative a2 being equal to c times a2, it has to be either that a2 is 0, because negative 0 is equal to a constant times negative 0, constant times 0, or c could be negative 1, right? Because negative a2 is equal to negative 1 times a2. Okay, and so what that means is there are the following possible solutions. You could have a1 be 0 and c be negative 1. You could have a2 be 0 and c be 1. You could have both a1 and a2 be 0. And then it doesn't matter what c is. Then the equations come out true no matter what c is. Okay, so these are the three possible forms for the eigenvectors. If a1 is 0, it doesn't matter what a2 is. a2 can be anything, so that's why I put in x here. Okay, now it happens that in quantum mechanics, the vectors that are used to represent physical states of a system have to be vectors with a length of 1. Right, so in the answer to the previous math problem, you can have a vector of the form 0x, but if we add the constraint from quantum mechanics that it has to be a vector with a length of 1, then this has to be 0, 1 with eigenvalue negative 1, and this one has to be 1, 0 with eigenvalue 1. That's the only way that the vector has a length of 1, and this one it can't be done. It can't be 0, 0 because that has a length of 0. Okay, here's another problem. So you might not have done that last one, but maybe you can do this one now. So what are the eigenvectors and corresponding eigenvalues for the operator 0, 1, 1, 0? So pause the video and see if you can answer that on your own, and then I'm going to come back and tell you the answer. Okay, so here's how you would solve this. So the eigenvector is by definition a vector that makes this equation true, right? So, and this is the eigenvalue. So the question is, what are the possible values of a1, a2, and c that make this whole equation true? Okay, and so if you just do the vector multiplication, multiplying this one by that, it's 0, a1 plus 1 times a2 goes here, which is a2. And then 1 times a1 plus 0 times a2 is a1, so that goes here. And then the right-hand side of this equation is just c times a1 and c times a2, so that goes there. If you look at this equation, you see that that implies that a2 is equal to c times a1, and a1 is equal to c times a2. And now think about how that could be true. Right, so if you think about that, the only way that can be true is c is equal to 1 and a1 is equal to a2. Or c could be negative 1, and a1 could be equal to negative a2. Okay, both of those make this system of equations work out. And so therefore, possible eigenvectors are vectors of this form. That is, a1 and a2 have to be the same. This could be any number, and this has to be the same number with eigenvalue 1. Or any number here and the negative of that number here with eigenvalue negative 1. Okay, now again, as I was saying in the previous slide, in quantum mechanics, the vectors that represent possible physical states have to have a length of 1. So add that constraint to this. We had this solution for the possible eigenvectors, but add the constraint that they have to have a length of 1. Then in that case, the eigenvector has to be this, 1 over the square root of 2 for the first entry and 1 over the square root of 2 for the other entry with the eigenvalue of 1. This is the solution because this is the only way to make the length of the vector 1. Okay, the length of the vector is the square root of this squared plus this squared. That's just from the Pythagorean theorem or the general distance formula. Okay, the length of this vector is the square root of this thing squared plus this thing squared, and that comes out to 1. Okay, so these are the possible solutions. 1 over root 2, 1 over root 2 with eigenvalue 1, 1 over root 2, negative 1 over root 2 with eigenvalue negative 1. Okay, and by the way, all this is in David Albert's second chapter, although he doesn't explain why you have these vectors. Okay, Now we have enough background to talk about what is the quantum mechanical algorithm. So quantum mechanics has a particular algorithm for predicting the results of experiments. And it's that algorithm that requires interpretation. It's that algorithm that people are arguing about what it means about the nature of underlying physical reality. The algorithm takes these mathematical objects, does certain calculations on them, and then from those calculations you get the probability of different possible experimental outcomes. Okay, so in the algorithm, the way that you represent a possible physical state of a system is with a vector. The vector has to have a length of 1, and these vectors are called state vectors. Okay, now a terminological note about this is when people refer to states, they're referring to a possible value that a variable could take on, or possible value of a property. When they refer to properties, they mean these things that could have multiple possible values. So position is a property. Being in Boulder, Colorado is a state, right? So because being in Boulder, Colorado is a specific value of your position. Okay, spin in the x direction is an example of a property. Being spin up in the x direction is a state corresponding to that property, right? The specific possible value of that property. Okay, observables are measurable properties, right? A property of a physical system that you could do some kind of measurement on. And these are represented by linear operators. The operators have to relate to the state vectors in the following way. If O represents a certain observable property, then the state vectors that correspond to definite values of that property are the eigenvectors for that operator. Okay, also, when a physical object's state vector is an eigenvector of the operator O with eigenvalue A, then A is the value of that property. Okay, these are some examples. So the property x spin, that's an observable property because you can do a measurement to determine the x spin of something. So that observable is represented by this matrix, the 1, 0, 0, negative 1, which appeared on a previous slide. The physical state of a system when it has x spin up is represented by this, the 1, 0 matrix. The physical state where it has x spin down is represented by this 0, 1 matrix. Okay, the y spin, that property, is represented by this operator, 0, 1, 1, 0, and being y spin up is represented by this particular vector, 1 over root 2, 1 over root 2. Being y spin down is represented by the vector 1 over root 2, negative 1 over root 2. Okay, and that was why I had you work out those problems on the previous slides where these things came out as the answers. Okay, this is a diagram representing the spin space. So that is, the spin space is the vector space in which the possible spin states exist. Do not confuse this with physical space, okay? The spin space is not a place that somebody could go. It's a purely mathematical space, right, where there are these vectors that represent possible states of the spin of an electron. Okay, it's two-dimensional. Now, as a side point that we're not going to talk about, they use complex numbers, not just real numbers in quantum mechanics. So it's actually a two-dimensional complex space, but we're not going to talk about that. So if you did the z-spin, you have to use imaginary numbers to represent the state for having z-spin up or z-spin down. But because imaginary numbers are confusing, we're just not going to talk about the z-spin. Okay, now here's an interesting thing to note about these different vectors. So note that the vector that represents a thing having x spin up is equal to this linear combination of the y up and y down vectors. That is, this is just a true mathematical equation based upon the previous descriptions of what these vectors are. The x spin up vector is just equal to 1 over root 2 times the y up vector plus 1 over root 2 times the y down vector. And similarly for these other things. So you notice that the vector that represents an object as having a particular x spin is identical to a combination of a particular y spin and a different incompatible y spin. So it's sort of like having x spin up is like kind of being half y spin up and half y spin down. Okay, and similarly here, except there's a minus sign instead of a plus. Similarly, having y spin up is like being in a combination of x spin up and x spin down. Having y down is a different combination with a negative instead of a positive combination of being x spin up and x spin down. Now, this is the basis for the uncertainty principle that you hear so much about. There's something analogous to this for position and momentum. They're related in a similar way. Right, so in the Heisenberg uncertainty principle that you probably heard about, if you heard anything about quantum mechanics, it said that you can't have a definite value of position and also have a definite value of momentum. Now, the uncertainty principle is in fact misnamed because the name of it makes people think that it's just that you can't know the position and the momentum at the same time, like it's uncertain what the position and the momentum are. But the actual basis for this principle is that the mathematical formalism contains no way of representing an object as having a definite position and having a definite momentum at the same time. In the same way that you can't represent an object as having x spin up and y spin up at the same time, because the x spin up is just equal to this combination of y up and y down. It's just like identical. This thing is the identical mathematical object as this, right? And there's, in this spin space, there just is not a vector that represents having x spin up and y spin up. And there is not any vector that represents any definite value of x spin and also a definite value of y spin. Okay, so that's analogous to the relationship between position and momentum. The position and momentum are represented in another vector space with higher dimension, but basically the problem is there is no vector in that space that represents having a definite position and a definite momentum at the same time. Okay, now this is about the dynamics of the state vector. This is about how the state vector for a physical system changes over time. Right, so there are two things. There's what the state vector does when you're not observing a physical system, and then there's what it does when you observe or make a measurement. So if you have a physical system that's not being observed and no measurements are done, it evolves according to this equation known as the Schrodinger equation. And here I've written a version of the Schrodinger equation. But what matters about this equation is just two interesting features. The first is that it's a completely deterministic equation. And what I mean by that is there's only one possible future evolution. If you're given the value of the wave function at a particular time and no observations are being done, there's exactly one possible future evolution. There's no chance, right? There's no multiple possibilities branching out. Second interesting thing about the equation is that it's linear. And what I mean by that is if you have a particular vector that would evolve, if you have a vector A that would evolve into a vector A prime, and also if vector B would evolve into B prime, then a linear combination of A and B would evolve into a linear combination of A prime and B prime. Or in other words, if you're in a superposition of these two states and you apply the Schrodinger equation to it, what should happen is it should evolve into a superposition of these states, right? That is, if you know what this initial state would evolve into and you know what the other initial state would evolve into, then you know what a superposition of the two initial states would evolve into. It would evolve into a superposition of the two final states. Okay, but according to kind of the standard way of thinking about quantum mechanics, there's a different thing that happens when somebody makes a measurement or does an observation of an observable property. So you have this observable O, and somebody does a measurement on it. Then one of two things happens. So you have a physical system that's in a particular state, so it has a determinate quantum state, which is a vector in the vector space, and let's say that the vector representing the state is A. If A is an eigenvector of O, then what happens is you measure the system and find it to be in that state. Right? So, for example, if you're measuring the x spin and your electron is already in the state x spin up, then the measurement will find it to be x spin up. That's it with probability 1. And furthermore, that state is not changed. So after you do the measurement, it's still x spin up. However, the weird thing happens when the state vector is not an eigenvector of the observable, right? So let's say you're measuring the x spin and it's not x spin up, maybe it's y spin up, so it has no determinate value of the x spin, according to the standard way of thinking about it. Then what happens is that the system will immediately jump into an eigenvector of that observable. It wasn't in an eigenvector of the observable, but as soon as you do the measurement, it jumps to such an eigenvector. And what vector it jumps to is randomly selected. Furthermore, there's a rule for the probability of different possible results. So the probability of it jumping to a particular eigenvector E is given by the square of the absolute value of the inner product of A with E. Right? So you multiply the current state vector times a particular eigenvector. Take the absolute value and square it, and that gives you the probability that the physical system will jump into that eigenvector. So for example, if you have a system that is y spin up and you decide to measure its x spin, what will happen is it will jump to either x spin up or x spin down, each with 50% probability. Okay, and if you do the calculations using the previous slide statement of what x spin up and y spin up are, you're going to verify that probability. Okay, and then the observer will observe the system to be in that state. So according to the theory, what happens is if you measure, so the physical system doesn't have a determinate value for a certain observable, but if you measure that observable, it immediately acquires a determinate value, and then thereafter you will find it to have that value. And this is where you get these statements that you hear about quantum mechanics, like it says that observers create reality. Well, what's the case is that the physical system has a particular value for the state vector. The state vector is always in a specific determinate value according to this theory. It's just that some of the specific values of the state vector don't correspond to determinate values for the observable that you're measuring. And so if you then observe it, then it switches to having a determinate value for that observable. And this is supposed to be a real physical change. Right, so the state vector is supposed to represent the actual physical state of a system, and that state actually changes when you do the measurement. Okay, and this is where chance enters into quantum mechanics. So the Schrodinger equation is completely deterministic, but what happens is when you do this measurement and the thing is not already in a determinate value for the measured property, what happens is Schrodinger evolution is violated. The system evolves in a way that's not according to the Schrodinger equation. It just immediately jumps to this randomly chosen state vector. This is referred to as the state vector collapse or the wave function collapse. And the idea that there are such changes is referred to as the collapse postulate. Okay, now notice why the collapse postulate is necessary. It's necessary because in reality, when you do observations, you find physical objects to be in definite states. When you try to measure the position of an electron, you always find it to have a particular position. And if you don't have the collapse postulate, then what should happen when you observe the position of a particle and it doesn't have a definite position? So if a particle is in a superposition of different positions and you measure the position, what should happen is you should go into a superposition of seeing the particle in one location and seeing the particle in another location. That is, that's what would happen if there was no wave function collapse. Okay, and now presumably whatever that would be like, that's not what happens. When you actually measure things, you always find them to have particular values. You, the observer, do not go into a superposition, whatever that would mean. Okay, now the Copenhagen interpretation is sort of the orthodox interpretation of quantum mechanics. It's the interpretation that people are talking about when you read a lot of weird stuff about quantum mechanics in the popular literature. So if you read one of these pop science books about what quantum mechanics tells us, where they tell you about how observers create reality and the world is fundamentally governed by chance and all that stuff, what they're talking about is generally the Copenhagen interpretation. This is not the only interpretation, but it is kind of the best known interpretation and sort of the orthodox view. Okay, so the Copenhagen interpretation says when you have a physical system whose state vector is equal to a linear combination of the state vectors corresponding to determinate states, then the physical object is in an indeterminate state. It doesn't have a value for some properties. So for example, electrons can be in a superposition of different locations, in which case the electron doesn't have a location. There's no fact of the matter about where it is located. Similarly for x spin, y spin, and so on. So if you have an electron that is x spin up, then it has no value for its spin in the y direction. It's not the case that it's y spin up. It's not the case that it's y spin down. The way David Albert describes this is he goes on to say it's also not neither and it's not both, right? So making it clear that it's contradictory. Okay, but whatever exactly this means, the thing is supposed to not have any particular value for the y spin. Okay, now that might not bother you so much because y spin is a purely theoretical property, but the theory also implies that you can have physical objects where there's no fact of the matter about where they are located. Okay, but it's not that they're outside of space or anything like that. There's an objective fact that they're in space, but there's no objective fact about where they are exactly. Okay, according to the Copenhagen interpretation, observers or measurements cause things to go into definite states for the properties that are being measured. Okay, now it's a corollary of this that observers or measuring devices, whatever this is, are somehow governed by different physical laws from the rest of the universe, because wave function collapses only occur when somebody does an observation or a measurement. If there's no observing or measuring going on, then Schrodinger evolution just goes on. Okay, now this gives rise to a philosophical question. Well, that would make you wonder, so what exactly constitutes a measurement or an observation? It's a little bit weird that it has this important role in fundamental physics. One view you might have is, well, maybe you have an observation when there's a conscious being who does something that would cause them to have a mental state representing the property, right? So like if you do something that would cause a conscious being to know the position of an object, that counts maybe as a measurement of position. Or another view, maybe the more common view, is it's just when you have an interaction with a macroscopic object. So if you interact with an electron in some way so that the position of the electron would get correlated with the location of some large macroscopic object, maybe that is what counts as a measurement. Okay, now if you had that view, of course, then you have this weird question about exactly how large an object has to be in order to count as macroscopic, right? Because there's different laws applying depending upon whether an object is macroscopic or microscopic. But this is a bit odd because there's not a fundamental qualitative distinction between being large and being small, right? So there'd have to be some weird threshold between the large and the small. Okay, now all of this also gives rise to another famous idea known as the Schrodingers Cat Paradox, or just the Schrodinger's cat example. Okay, so this is an example you might have heard about in some of the popular discussion of quantum mechanics. In the example, you imagine that there's a cat in a box, and there's a device that is hooked up to, there's a sample of radioactive material, and there's a Geiger counter. And there's a 50% probability of a sample of the material decaying and sending off some radioactive particle during a given time period. And so the Geiger counter is connected up to this device such that if it detects a radioactive decay, it will break a bottle of poison, and that will kill the cat. And if it does not detect a radioactive decay, then nothing will happen, so the cat will be fine. Okay, and according to quantum mechanics, it can be completely random whether or not the radioactive decay occurs. But again, according to the Copenhagen interpretation, the radioactive material is going to be in a superposition of being decayed and not decayed until somebody measures it. So it's in a closed box, nobody's observing it. It's going to be indeterminate whether it decayed or not. And then as soon as somebody does a measurement, it's going to be determinate. And then you have the question of, well, so does that mean that the cat will be in a superposition of being alive and dead? It'll be half alive and half dead or something, whatever this means, which doesn't seem to make any sense. Or you might wonder, oh, is the cat itself enough of an observer? Like, does the cat have enough consciousness to collapse the wave function? And so you get these weird questions. And this example was devised by Erwin Schrödinger, one of the founders of quantum mechanics, because he thought the Copenhagen interpretation was insane and that it didn't make sense to talk about these things being in superpositions. And so he devised this example so that you'd have this reaction that it was implausible that there could be a superposition, right? You're supposed to think, no, the cat couldn't be in a superposition of being alive and dead. That doesn't make sense. Okay, now I'm going to go back to an experiment that we described in the previous lecture and just kind of walk through what the Copenhagen explanation of this experiment is. So if you look at this diagram, you imagine that you feed electrons in at the bottom into this X spin box. If you take an electron that is Y spin up, you feed it into the box, and you expect that it will go either on the upper path or the lower path. It will wind up at point E, and then it will go into a Y spin box. And what we observe is that if you don't disturb it in any way, it's going to go into the Y spin box and come out Y spin up. That is, if it was Y spin up when it went into the device, it comes out Y spin up here. If it was Y spin down, it somehow goes through the device and comes out Y spin down over here. Why does that happen? Okay, so this is the explanation. So being Y spin up is equivalent to being in this superposition of X spin up and X spin down. Now, if you had an electron with X spin up and it went into this box, it would go on the upper path and it would wind up at the end in this state. Okay, and what this means is being X spin up and being located at position E. If you had an electron with X spin down, so this is the state vector representing being X spin down, it would evolve into being X spin down and being located at position E. Okay, so given the linearity of Schrödinger evolution, that means that if you had an electron that was in this linear combination of X spin up and X spin down, it would evolve into being in a linear combination of being X spin up and located at E, and being X spin down and located at E. That's just because the evolution is linear in the sense described on a previous slide. Okay, but notice that this state, so this is the final state if you didn't do any observations, so there's no wave function collapse. So it should wind up in this state by the time the electron is over here. And notice that this state is equal to this. 1 over square root of 2 X spin up plus 1 over square root of 2 X spin down and located at E. Okay, but also notice that this state, 1 over root 2 X up plus 1 over root 2 X down, is just equal to the state vector for being Y spin up. So what that means is the electron evolves into being Y spin up and located at E. And so that's why if you then feed it into this Y spin box, it comes out being Y spin up. Okay, now if you block the lower path, then you block step 3 in the previous reasoning, right? That's the step that says if you fed in an X spin down electron, it would evolve into being X spin down and located here. Also, if you place a measuring device somewhere to find out which path the electron takes, then according to the theory, that is going to cause a collapse of the wave function. So if there's some kind of electron detector that verifies that the electron went on the upper path, then that collapses the wave function. So the physical state of the system changes to being x spin up and on the upper path. Or with 50%, so it's a y spin up electron, there's a 50% chance that that would happen. It would collapse into x spin up and being on the upper path, and a 50% chance that it would collapse into being x spin down and on the lower path. Okay, but so that collapse would mean that when you got to point E, only one of these wave functions would be present. And so the electron would be either x up or x down, and then when it gets fed into the y spin box, it's just going to be completely random whether it comes out y spin up or y spin down. Okay, so now these are the philosophical questions that I want you all to think about as I conclude the video. Is the Copenhagen interpretation a good interpretation of what's going on? So you should wonder about whether objects can actually be in indeterminate states, as this interpretation says. You should wonder if the world is indeterministic, that is it governed by chance rather than being deterministic? And by the way, although these two words sound the same, indeterminate and indeterministic, those are very different concepts. Indeterminate means you can have a property where there's no specific value of it. There's no fact about exactly what state the thing is in at a particular time. Indeterministic means you can have a case where there are multiple different possible future evolutions from a given point, and it's just a matter of probability which one happens. Okay, being indeterminate looks like it might be a violation of logic. Being indeterministic, of course, is not a violation of logic. And the other interesting philosophical question is whether observers or measurements might follow different physical principles from non-observers or non-measurements, and if so, how should we understand the notion of an observer or measurement? Does this mean that consciousness plays a special role in physics, or is it just a matter of microscopic versus macroscopic objects? And then what exactly is the distinction between micro and macro?